A power sliding door lives or dies on one cable drum and an 80-millisecond reflex. Where the drum and the same part that moves the door blinds the safety sensor. The fix comes last. Here's why this matters. That panel weighs over 100 pounds and it moves under power, with kids and hands in its path every single day. When it goes wrong 3 ways. It won't close, it reverses for no reason, or it closes on someone. Those aren't rare glitches. They fill dealer complaint logs and they've driven federal recalls. And the fix isn't a new sensor. It's simpler and almost nobody checks it first. Start with how the door actually moves. Open the panel and you don't find a big motor shoving the door. You find a spool. A small motor turns a drum, and wrapped around that drum is a steel cable that pulls the door along its track. Wind the cable in, the door slides one way. Let it out, it slides back. Here's the clever part. 2 cables share that one drum, an open cable and a close cable. They wrap in opposite directions, so as the motor turns, one cable wins tight while the other pays out. One drum, 2 jobs, always in balance. So why a spool instead of a straight-toothed bar, the kind of rack-end gear you'd expect? 2 reasons, and they both come down to space. A minivan door slides a long way, often over 2 feet, and a rack that long would need a track just as long bolted inside the body. A drum packs all that travel into a coil the size of a coffee mug. And the door's track isn't straight. It curves outward at the end, so the panel swings clear of the body before it runs back. A rigid rack fights a curve. A flexible cable follows it, bending around guide rollers wherever the path bends. So the drum earns its place, compact and happy with a curved road. That's the whole moving system. 1 motor, 1 drum, 2 cables, a curved track. Simple, elegant, and carrying far more responsibility than it looks. Now the trouble. This whole system depends on that one cable staying exactly the right length and sitting exactly in its groove. And cables don't stay that way. Over tens of thousands of cycles, steel cable stretches. Strands fray. Sometimes the cable jumps out of its groove on the drum and rides up on itself. Meanwhile, the drum's own parts wear. The plastic body, or the small clutch that lets it slip if the door hits something. Any one of those and the geometry drifts. Watch what a stretched cable does. If the close cable grows even a little slack, the door reaches the end of its travel but doesn't pull hard enough to snap the latch shut. So it binds. It jerks. It stops an inch short and sits there unlatched. Here's the part most people miss. This system is calibrated tight. The controller doesn't just run the motor blindly. It learns the door's normal travel, how far it should move and how much force that takes. It memorizes the healthy trip. So when a worn cable adds drag or a frayed strand catches, the door needs more force to move than the controller expects. And more force than expected has a specific meaning to this computer. It means something is in the way. The controller can't tell the difference between a child's arm and a tired cable. Both feel like resistance. Both read as an obstruction. So a door that's simply worn out starts behaving like a door that's being blocked, stopping, reversing, refusing to close. The mechanism is failing, but the symptom looks electronic. Hold that thought because it's about to matter a lot. So how does the door know a hand is a hand? This is the reflex the whole safety story rests on. When the door meets resistance, a sensor flags it and the controller throws the motor into reverse, in tens of milliseconds. Call it the 80-millisecond reflex. Why 80 milliseconds? Because it has to beat you. A human takes about 1/5 of a second, 200 milliseconds, just to notice pain and start pulling back. The door has to decide and reverse before your own nerves finish that message. If it's slower than your reflex, it crushes before it releases. Faster and it lets go while you're still flinching. That's the entire margin between a safe door and a recall. Now, how does it actually feel the hand? 2 ways, often together. The first is a pressure-sensitive strip running along the door's leading edge. Squeeze it and it reports a touch. Think of it as a long, thin doorbell down the closing face. Press anywhere along it and the door hears it. The second way needs no strip at all. The controller watches the electrical current feeding the motor. A motor working harder pulls more current, that's just physics. When something blocks the door, the motor strains, current spikes past a set threshold, and the controller reads that spike as an unexpected load. Edge strip, current spike, or both, the door is constantly asking one question. Is this trip normal, or did something just get in the way? When the answer is in the way, the 80-millisecond reflex fires and the door retreats. That reflex is the hero of this story. But notice what it's listening to: force and current. Remember that. It's about to be the villain too. Here's the trap. The reflex listens for force and current, and a worn drum produces exactly those. Follow the failure. A frayed cable catches. The door drags. The motor strains and pulls extra current, the same spike a real pinch makes. The controller can't tell the two apart, so it does the safe thing: it reverses. The door false reverses, backs off, and refuses to close over and over with nobody near it. Owners call it a ghost. It isn't a ghost. It's a worn cable wearing the sensor's costume. That's the annoying failure. Now the dangerous ones. Run the same where the other direction. Suppose the drag builds slowly, or a sensor degrades and its threshold drifts. Now real resistance, an actual arm, doesn't cross the line the controller is watching. The door feels a hand and calls it normal. It doesn't reverse. It keeps closing. That is the crush hazard, and that is what turns into a federal recall. A door that should reverse and doesn't. Here's the point that ties it together, and it's the one almost everyone gets backwards. These two failures aren't separate problems. They're the same problem. The drum feeds two things at once: the door's motion and the force signal the safety logic reads to protect you. Wear the drum and you corrupt both. You break how the door moves, and in the same stroke you blind the sensor that's supposed to catch a hand. One worn part. Two failures, one merely maddening, one genuinely dangerous. And they walk in together because they were always the same wear. So here's the takeaway, the thing to actually walk away with. The door lives or dies on drum health, not because the drum is fragile, but because it carries a double load. It moves the door and it feeds the force signal the safety brain trusts. Healthy drum, honest signal. Worn drum and the same reflex that's supposed to save a hand can't be believed. Which is exactly when a manufacturer issues a recall. It's the reflex they can no longer trust to reverse. Now the practical read, and it's the move almost nobody makes first. When a power door reverses for no reason, backs off, and won't latch, the instinct is to blame the electronics. Replace the sensor, swap the module, chase the computer. That's usually backwards. A random reversing door is far more often a stretched, frayed, or slipped cable feeding a false spike than a dead sensor. So the biggest lever is this: fix the mechanism before the electronics. The single first step costs nothing. Before anyone orders a part, have the cable and drum inspected for stretch, fraying, and a jumped groove, and the track cleaned and lubricated. Cheaper than a control module, and it targets the real culprit. Get the drum honest, and the 80-millisecond reflex starts telling the truth again. So it comes down to this. One cable drum and one 80-millisecond reflex decide whether the door is a convenience or a hazard. Get the drum honest, and both the motion and the safety come back. But the drum is only half the door. The latch, how it grabs and holds, and the separate full-open recalls where doors swing wide and won't stay put. That's its own mechanism and its own set of failures. That's next.